Hey, Dr. Clark here as always, and in this video we're going to learn how to compare multiple means using a simulation-based approach. Let's get started. So how do you compare more than two means at the same time? That's what Chapter 9 is about. This is sort of the idea, one example, I think this is from an agricultural data. They had some different amounts of chemicals that they could put on or something, and then they compared their yields for the different things. And they wanted to know, was this one different than that one, from that one, from that one, right? So how do you compare multiple means to each other when you got a bunch of different quantitative data, more than just two variables? All right, so maybe you've got, Core 140 and there's 6 sections, and you want to compare the mean exam grades for the 6 sections. Well, there's a lot of different ones to compare. You could compare Class A and B, or A and C, or B and D, or F and G, or B and E. There's actually probably like 20 different ones to 24, I think, different pairwise comparisons. And if you're using 0.05 as your significance level, well, that means if you do 20 comparisons and there's 20% and there's a 5% chance of having a false alarm, then you could easily just reject the null hypothesis when it was, essentially by accident, by a false alarm, if you do too many comparisons. So that's what we got to avoid against here. So what we really need is an overall test that examines the big picture instead of just each pairwise comparison until we find two that are different. And this is similar to what we did in Chapter 8 with the chi-squared statistic that put all the proportions into one test. Well, now we got to put all the means into one test. The hypotheses are going to be that the true long run or population means are all the same for all the groups, or that at least one of the true long run or population means is different from the other. So we're talking about multiple means here. So mu1 equals mu2 equals mu3 equals mu4. Either they're all the same, or at least one of the mu's is different from the others. Okay, that's kind of how you would write the hypotheses. And we're going to do this using the MAD statistic, which is actually the same as what we did with multiple proportions. But this is how it works. You just do the same thing. You take your average from sample 1 and your average from sample 2, compare them, take your average from sample 1 and sample 3, compare them, sample 2 and sample 3, compare them, and then add up the absolute values, divide by 3. So find the average of the differences of the absolute values of the differences, I guess. But if you had 6 different means, then there would be a whole bunch of these to do. So you'd have 15 pairs, so you'd want the applet to do it for you. Okay? But the general rule is the bigger these differences are, the bigger this MAD statistic will be, and therefore the stronger the evidence that one of the true means are different. Because this is coming from the data, right? What we are hoping to find out is that one of the true population means is different. But these are going to be X bars right here. And so the question is the difference we observed in the sample, with the sample X bars, are those differences big enough for us to conclude that the population mu's, the parameters, at least one of them is different? Okay, and then we'll just simulate it. So we'll let the applet basically take all our quantitative data, and let's say we have 3 explanatory variables, 3 choices, but it could be 6 or whatever, and we'll just randomly deal out those numbers into 3 piles or 6 piles. We'll compute the means for each group, the X bars, and then compute the MAD statistic. So we can see what kind of MAD statistics would this data generate if we just did it by random chance. And then we can repeat that 1,000 times to create a null distribution. And then we can compare our MAD statistic from the actual data to what happened by random chance in the null distribution. And either our statistic from our data will be way outside the norm or just typical from what could happen by random chance if you randomly dealt those quantitative datas into 6 piles or 3 piles or whatever and computed the MAD. And then if it is significant, that's when we follow up with pairwise confidence intervals to say, okay, we know that there's a general trend of difference. Can we figure out which ones are different? Is there 1 or 2 that are standing outside the rest? Okay, and we'll see how to do that in the next video.